Alrighty, time for some ionization energy. So we've discussed the size trends for both atoms and ions. Again, it doesn't really matter if you think of them as atoms or ions, because the way that I have you learn them, it really takes care of them either way. But what we're going to get into now is ionization energy. And actually, if you can do your size trends, the ionization energy is just one little added fact, and then you can do ionization energy pretty easily, in my opinion. So let's first start with what ionization energy is. And if you look at the definition, the term ionization energy, it is the energy needed for something to become an ion, but it's a little more specific than that. So it's energy needed to remove the outermost electron from an atom. So we're talking about causing atoms to lose electrons, how easy it is to take an electron away from an atom. And that idea, I like to use an analogy for this idea, because I think that it's easiest to understand these types of things with analogies often, because I can't show you an atom. I can't show you an atom holding onto its own electron versus another atom holding onto its electron and show you which one's holding on more tightly. So I like to use the analogy of like a mother. A mother might be the nucleus, and when you have a newborn, that would be like an electron that's really close to the nucleus. When you have a newborn baby, you're always holding it, you're holding on tight. If you're walking up the stairs, you squeeze a little harder than you would normally. You don't want anything to happen to them. You're not going to let anybody take your baby away from you, because things that are close to the nucleus, electrons that are close to the nucleus, it's really difficult to remove them, because that nucleus has so much control over that electron. It makes it very difficult to remove them. Whereas if you have, say, a teenager like you guys, you represent an electron further out. Maybe it's on the third energy level or the fourth energy level, further away from the nucleus. And the nucleus doesn't have as much control over those electrons, whereas they still control them to some degree, as I'm sure you all agree. Your parents still have some control, but the control loosens up as you get older and you move further away from the nucleus. And so the idea of ionization energy is, how hard is it to remove that electron? So how hard is it for somebody to take a newborn baby away from a mother versus a mother to let an 18-year-old go off to college? It's obviously going to be easier to let your 18-year-old go off to college. And so you'll see that in the next part of your notes, it says that if you have high ionization energy, it means it's holding on tightly. Okay, that's like the baby, the mother and the baby. Whereas low ionization energy means it's not holding on as tight. It's still holding it. Nucleuses still hold on to their electrons, but it's not holding on as tight. So it's going to be harder to take an electron away from something that has a high ionization energy that's close to the nucleus than something that has a low ionization energy. And by high and low, obviously those are relative terms. High means takes more energy, low means takes less energy. Now, as a general rule, to make it easy for you to sort of think about this and think about it in the context of the atomic and ionic size, if you have a bigger atom, the ionization energies for those valence electrons are going to be smaller. Okay, we're talking valence electrons always, because if you look back at the definition, it said the outermost electron. So remember, that's the valence electron. So if you have a bigger atom, those valence electrons are further from the nucleus, you're going to have smaller ionization energies. Whereas if you have smaller atoms, those valence electrons are closer to the nucleus, and they're going to have larger ionization energies. Now, there are trends. You know how I feel about trends. But the trend, again, can be used as a way to check yourself. The why, much more important. So the trend of ionization energy is that ionization energy decreases as you move down a group. That makes sense, because we also know as you go down a group, atoms get bigger. And we said the bigger it is, the lower the ionization energy, which is really what the explanation is there. Okay, so when you're explaining this, you should be using size as your backbone for your explanation, and then adding the part, about why that is the case. The closer you are, the more the nucleus has control. The further you are, the less control the nucleus has. Now, the second trend is similar. It says ionization increases as you move from left to right. Well, we know as we move from left to right, atoms get smaller. So the smaller they are, the higher the ionization energy. So again, that is our reasoning. And we should really be focusing on this reason part as opposed to focusing on the terminology or the trend that's written there for you. Because again, the trend doesn't give you a reason. And we need to be able to explain our thoughts here. Okay, the AP wants explanations. So we worked on explanations explanations of atomic size and ionic size, what's important to include, and that's what we're going to look at here with some examples, because you need to be able to, correctly explain this. So let's go through some examples. So the first question says, what has a larger ionization energy? Now, having even shown what we're comparing, before you do anything, I would immediately write down for yourself, and I can't get my tools to work right now for some reason, but the larger ionization energy means a smaller atom. So right over here, write for yourself smaller atom, so that you're thinking, okay, I need the smaller atom. And then if we look at the question, we have potassium and we have sodium. So find potassium and find sodium on a periodic table. If you don't have a periodic table with you right now, pause this and then go get one, because you really need to be looking at one. So sodium and potassium. So we're looking for remember, larger ionization energy means we want the smaller atom. So out of sodium and potassium, sodium is the smaller atom. Okay, so that's going to be our initial answer, is that sodium is going to have a larger ionization energy. And then for your reasoning, here's what we need to do. You're going to say that it's the smaller one. You don't need to explain why it's the smaller one. You just need to say that it is the smaller one. And then you're going to discuss why smaller means higher ionization energy. So my explanation says this is a smaller one, and therefore it requires more energy to remove the outermost electron, because the electrons are closer to the nucleus, giving the nucleus more control over them. So there's a lot of facets to this. You need to have all those facets there. You need to say it's the smaller one. Again, don't need to explain why. So you don't have to get into energy level explanation as to why it's a smaller one, but do notice that I talk about it being closer to the nucleus, those electrons. So you do have to have that piece in there, and then you can talk about the nuclear control as the third element that needs to be there. So if you didn't get to write all that down, pause it as I move on, before I move on to the next example, because you really need to make sure that the explanation part is there. All right, next example, I think we're still doing larger ionization energy. So we want the smaller atom out of these two. So we look at calcium and we look at bromine. They're on the same period. Okay, so same period tells us that we don't know yet, but because they're in the same period, we want the one with more protons is going to be the smaller one. So Br is going to be the smaller of the two. So you notice in my explanation, I'm going to say that this one is the smaller one, and therefore it requires more energy to remove the outermost electron, because the electrons are closer to the nucleus. This time the electrons are closer to the nucleus because sorry, I'm trying to get this out of the way for you. This time it's closer to the nucleus because the protons are pulling them in more. It's not an energy level difference. The protons pulling in more, but it's still closer to the nucleus regardless. And we said all you have to state is that it's smaller. You don't have to explain the real reason why that one is smaller. And so that's going to be what's going to need to be included in this explanation. Okay, so you can do ionization energy just like you do size, and keep that size as your backbone for this, and it will make these problems a lot simpler. It's now time for electron affinity. I don't know, sorry. Sometimes I get silly. So, electron affinity. Let's start with this word affinity. Before we do anything, before we get into any definitions and for anything, in English class, you've learned this word affinity before. Affinity means a liking of something, and affinity can be used for things other than electrons. Obviously, in our case, it's talking about the liking of electrons, but I might say that I have an affinity for Chinese food, or an affinity for Chipotle, or an affinity for Diet Dr. Pepper. I'm actually a little worried here because all my examples were food. All right, I have an affinity for my children. I have an affinity for my husband sometimes. No, I'm just kidding. But an affinity means a liking of something. And so that's really going to help you understand what this term means. So if we take a look at the definition of electron affinity, it says the energy change that occurs when an atom gains an electron. So this is the liking of an electron, how much an atom wants to gain an electron. It's a little different than ionization energy, in that ionization energy was taking into account how much energy it took to remove an electron. And electron affinity says an energy change. Okay, it always takes energy to remove an electron, but sometimes when atoms gain an electron, they actually get to give off energy, and you'll see that by negative values on the electron affinity table. Unfortunately, electron affinity is not as straightforward as size and ionization energy, because those ones can be based on the size of the atom, which is very trend based. It's very much based on the location on the periodic table, whereas electron affinity is more, you could call it emotional. okay, because it's about affinity. It's more emotional for an atom. It's about whether or not gaining an electron would be good for that atom or not. And that's what we need to get into, and that's what we need to look at. So make yourself a note that for electron affinity, we are not using what we've been using. Size, ionization energy, those two things go hand in hand. Electron affinity requires a little bit different frame of reference of thinking, okay? So it's how much an atom likes to gain an electron. Now, you can see here it says atoms with high attraction for electrons will have a more negative value for their electron affinity. Remember, the definition is the energy change associated with gaining an electron. And anytime a reaction can give off energy, that means it's becoming more stable. And remember, giving off energy is exothermic, and exothermic is negative. So if it has a more negative value, that means that it really wants that electron. Seems contradictory, you know, like more negative, but it means it wants it, because if it gets to gain it, it gets to give off a lot of energy, and that is very beneficial. You can look at the electron affinities for the halogens in group 7A, and they all really would like to gain an electron because they get to become like a noble gas. So you can see that their values are very negative. Okay, so the more negative the value, the more likely it is for that atom to gain an electron. You'll see some of them also have positive values for their electron affinities, and the reason for that is that some things don't want to gain an electron. You know, noble gases don't want to gain an electron. Metals, they don't want to gain, they want to lose. So gaining an electron wouldn't be good for them. So you'll notice that those ones, you have that situation where you have a positive value because you actually have to put energy in to try to force it to take that electron. Let's go ahead and compare B and F based on their electron affinities. And again, with that same thought in mind, if you take a look, you see that fluorine has a more negative electron affinity because we know fluorine is one electron away from becoming a noble gas. And so if it gains that electron, it gets that stable configuration, and it's going to be more stable, therefore needing less energy to exist. So it's going to give off more energy. So you can see that comparison between boron and fluorine. Now, that one's pretty straightforward because boron, you know, is way over on the periodic table from fluorine, and fluorine's only one electron away. Boron's kind of in the middle between whether or not it wants to gain or lose, hence why it's a metalloid. But with fluorine, it's pretty straightforward. Not all of them will be like that, so we have to know what's most important to look at. So you're going to have some rankings that you need to rank your electron affinity thoughts based on. The first thing you're going to do whenever you're asked about electron affinity is look at the two things you're comparing. If you have a noble gas in that pairing, then it's always going to have the lowest electron affinity, the lowest liking for electrons. Think of electron affinity like that. So it always have the lowest one, which is the most positive value. So when I say lowest electron affinity, I'm saying most positive value, meaning we have to force noble gases to take an electron. They are not going to give off energy when you do that. They are not happy about it. So if you want them to take it, you're going to have to force it upon them. Okay, think about forcing a 3-year-old to eat broccoli if they don't like broccoli. You know, you're going to have to put a lot of energy into getting that to happen. And that's the first thing you want to look for. If it's a noble gas, it's a no-brainer. You know that the noble gas will always have the lower affinity out of the ones in your pair. Now, if you're not looking at a noble gas, one of them is a noble gas in your pair, then we're going to have to look for other things. The second thing you'll look for is nonmetals. Say you're comparing a nonmetal to a metal. So you know that the nonmetal will have a higher electron affinity because nonmetals actually want to gain electrons, whereas metals do not. So the next pairing you're going to look for, so you're going to look for noble gases first, then you're going to look to see if you have a nonmetal-metal pairing. If that doesn't help, so let's say you look at it and it's two nonmetals. So obviously they both want to gain electrons if they're both nonmetals. So what you're going to do is compare and look excuse me, at which one's closest to becoming a noble gas. Whichever one's closer to becoming a noble gas, that's going to be the one with the higher electron affinity. But sometimes, maybe we're comparing F and Cl, they both only need one electron to become like a noble gas. So very last case scenario, then you can actually use size, and the smaller one will have the higher affinity because the nucleus can pull that electron in more tightly to that nucleus. So we definitely have some things we need to learn with electron affinity. Luckily with size and with ionization energy, they all revolved around the same concepts, but for electron affinity you have to be thinking about some other things. So look at your pairing, see if you have a noble gas. If you do, the noble gas will be the lowest. See if your pairing is a metal-non-metal pairing. If it is, the one that's a non-metal will have the higher electron affinity. It wants electrons. If you're comparing two non-metals, whichever one's closer to becoming a noble gas will have the higher affinity. If they're both the same number of electrons away from becoming a noble gas, then the smaller one will have the higher affinity, because the smaller it is, the closer the nucleus is to that shell to be able to pull that electron in. Okay, so let's go through a couple of examples just so you can see them. So the first question says, which has a higher electron affinity? So which one wants the electron more? That's what the question's asking. You need to learn to think of it that way. Which one wants the electron more? So whenever you see higher electron affinity, make yourself a little note next to it. Wants electron more. So we look at this pairing. We don't have a noble gas, but this is a metal-non-metal pairing. So the answer is going to be the non-metal, okay, always. Higher affinity is going to be the non-metal. And the reason is because the non-metal only needs to gain an electron, whereas sodium would rather lose. So gaining an electron would be bad for sodium. It wants to lose, so you're going to definitely want to answer chlorine on that problem. Next problem, we have neon and bromine, and they asked which one will have the smaller electron affinity. So which one doesn't want to gain an electron? And you see immediately noble gas, noble gas. So noble gas is going to be the answer. Noble gases don't want to gain electrons. They will always have the smallest affinity. And I won't ask you to compare two noble gases to each other. Okay, it'll be a noble gas and either a metal or a non-metal to be comparing. So that one's going to be Ne. All right, O and F, which one has the largest electron affinity? So largest electron affinity means which one wants an electron more. If you look, oxygen is 2 away from becoming a noble gas. They're both nonmetals. Oxygen's 2 away, fluorine's 1 away. So the answer, oh, look, little reminder, more negative value. So the answer is going to be fluorine. And fluorine, it's going to be because they're both non-metals, but fluorine's closer to becoming a noble gas and only needs to gain that 1 electron. Now here's the last scenario that we would get to the very last reason for. We don't have a noble gas. We have two non-metals being compared. They want the higher electron affinity, so the one that wants the electron more. And the problem is I and Cl are both group 7a, so both of them want to gain electrons, but chlorine is going to be the smaller of those two, and the smaller of those two is going to be the one that wants it more if they're both the same distance away from becoming a noble gas. So that's going to be your reasoning there. Now I do want to reiterate to you that periodic trends are not 100% accurate. Okay, they are trends, and trend means that most of the time it works, some of the time it doesn't, and so you will see exceptions if you're ever looking at an actual table, but the AP test doesn't give you tables. They just tell you the information and ask you to use the trends as described to be able to figure it out what the answers are. Okay.